Okay, hello everyone. Welcome back to the Colchin seminar in differential algebra. Today it's our pleasure to introduce Orla McGrath, who will talk about dimension polynomials for partial affine difference algebraic groups. Thank you.
Thank you for the introduction and for the invitation to speak. So I'm a PhD student at the University of Leeds under Dr. Mikko Vidma. And today I'm going to talk about some results from a paper which I recently put on archive. I have the code there on the screen if you're interested. So essentially, I'm researching difference algebraic groups and some finiteness properties of them. And in particular, we can find the existence of a dimension polynomial. A lot of this work was done by my supervisor in a 2022 paper in the ordinary case, and I've generalized the results to a partial case. There we go. I'll start off with all the necessary preliminaries from partial difference algebra. I'll then move on to difference algebraic geometry, and in particular difference algebraic groups, and then talk about the results from the paper. So to start off with, in our basic setup, we have a difference ring, which is a ring together with these pairwise commuting endomorphisms. So from now on, I'll put sigma in place of difference just for brevity. And we will always, n will always be our number of endomorphisms. So when there's one endomorphism, it's the ordinary case, and when there's multiple, it's the partial case. Similarly, you can see the analog, it's a discrete analog to differential algebra. And we might call these endomorphisms our basic endomorphisms. So many notions from standard algebra have their difference algebraic analogs. So for example, a difference field is a difference ring whose underlying ring is a field. And we can see an intuitive example, which is the field of rational functions in n variables. And here our jth endomorphism shifts the jth coordinate by 1 in the function. And this is kind of the intuition. A lot of the time we might think of these maps as sort of shifts. Carrying on with our standard difference algebra, a morphism of difference rings is a morphism of the underlying rings that respects the difference structure on both of those difference rings. So there is a slight abuse of notation here. Really, sigma would be a set of endomorphisms on R or a set of endomorphisms on S. This just means there's a bijection between the sets of endomorphisms on each of these rings. And similarly, we have a difference ideal of a difference ring, which is an ideal of the underlying ring that is closed under each of these basic endomorphisms. So an open problem in difference algebra is still finding the exact classes of difference ideals that are finitely difference generated. And there are some conjectures that are still kind of waiting to be proven or disproven. So in this talk, I'll introduce a class of difference ideals that are finitely difference generated. So in order to do that, we need to consider what is a difference ideal that is generated by some set. And we'll just introduce some notation to make this a bit clearer. So hopefully you're happy that because our endomorphisms commute with each other, any composition of them can be written kind of like this. We can put them into the nice order. So any element of this set T sigma, we can consider to be an endomorphism of our difference ring R. And we call these elements transforms of the ring. So we have our basic endomorphisms, and then we have our transforms, which are compositions of those. This then allows us to consider the difference ideal generated by some set, which we use square brackets to denote this. And this is now the ideal, not just generated by all the elements of F, but also generated by every transform of every element in F. And of course, we would say that a difference ideal is finitely difference generated if it's generated by some finite subset in this sense. Carrying on, a difference K algebra If R is a K algebra and both R and K have different structure, if that K algebra structure and the different structure are compatible, as in if the morphism is a morphism of difference rings, then we call R a difference K algebra, or we write it as a K sigma algebra. Then similarly, as with the ideal, we can consider a different subalgebra that's difference generated by some set. Now we use curly brackets to denote these difference algebras. And this is the difference algebra generated not just by every element in F again, but by every transform of every element in F. And similarly, as we'd expect, a difference algebra is finitely difference generated if it's generated by some finite set as a difference algebra. So where algebraic geometry is the study of zero sets of polynomials, difference algebraic geometry, we're going to be studying the zero sets of difference polynomials. So a difference polynomial is a polynomial not just in the indeterminates y1 to ys, but in the indeterminates where we have each transform of these. So we have a polynomial ring in infinitely many variables. And this is naturally, well, of course, it's a K algebra, and then it has a natural difference structure. Because the sigma ring K is a difference ring, we can extend the way that those endomorphisms act on K to act on the polynomial ring, the difference polynomial ring, in kind of the expected way. For example, sigma 1 will map y1 to the indeterminate sigma 1 y1, and so on, in the natural way, based on the naming of the variables. So we will now have kind of everything that we need from difference algebra, in particular, difference ideals, difference algebras, and difference polynomials are going to be the main tools that we're going to be using. So we're ready to move on to difference algebraic geometry. I'll start off by just giving a review of an algebraic group before we describe the difference analog to this. So some people might consider this to be the functorial approach to algebraic groups and affine schemes. So I'm going to, for me, an algebraic group over any field is a functor which takes a K algebra and returns the zero set of some set of polynomials evaluated in that K algebra. In particular, an algebraic group for each K algebra R, we need G of R to be a group. The way that this works is that the polynomials can only take certain forms in order to make sure that their zero set is in fact a group. And we can consider, we might call this either the coordinate ring or the representing algebra of an algebraic group. There's a few ways we can think about this intuitively. You can either think about it as maybe the ring of functions on your algebraic group. If you're aware of algebraic groups, maybe we can see that choosing an element of GR for some K algebra R is equivalent to choosing a K algebra morphism from our algebra into R. So we actually have a dual equivalence between our algebraic groups and these finitely generated K-Hopf algebras. So the Hopf structure is purely when we have group structure on the geometry side, this is reflected in Hopf structure on the algebra side. So this is what I said. I kind of said those polynomials would need to take certain forms, and that form is that they would need to generate a Hopf ideal. So you can see some immediate examples of algebraic groups, which I'm sure we've seen. The additive group, of course, for any K algebra, it's implicitly an additive group. So this would be considered the zero set of just the zero polynomial. It returns the K algebra itself. The multiplicative group, which returns the invertible elements in our K algebra. And the way that we would kind of define this as a zero set of polynomials is we would need to have two elements of our algebra that are inverses to each other. And the general linear group for some m greater than or equal to 1 takes a K algebra and returns the set of invertible m by m matrices with entries in R. And hopefully you're happy that this can be defined as the zero set of polynomials because the determinant of a matrix is just a polynomial. And we're going to talk a lot more about the general linear group coming up. The last thing that we're going to need from just standard algebraic geometry is the notion of a closed subgroup. So if we have two algebraic groups, which we know are defined by some polynomials, let's say E and F as our sets, if E is a subset of F, essentially H is the zero set of, it has all the polynomials defining G and extra polynomials. So hopefully you're happy that this would mean that H is a subfunctor of G. So H is a subfunctor that's an algebraic group, and these algebraic group structures are kind of compatible. We say that H is a closed subgroup of G. When we are thinking, say, for example, about all the closed subgroups of an algebraic group G, really there's no need to kind of impose those polynomials in E. Again, they're already imposed because we're just looking at subgroups of G. And instead, we're only worried about the kind of extra things that we need to also define H. So the way that we kind of formalize this is H is defined by some ideal of the coordinate ring of G. So this would actually, this ideal here would be the image of those polynomials F in the coordinate ring for G. And again, because H has group structure, this defining ideal H has Hopf structure. So we again get this correspondence between closed subgroups of an algebraic group and Hopf ideals of its representing algebra. Okay, and now we're ready to kind of do the whole thing again, but in the difference setting. So we're now working over a difference field, and for the rest of the talk, we're going to be assuming that K is a difference field. So now we can consider difference polynomials over K. And then a difference algebraic group is just the zero set of some difference polynomials over K. Again, where for every, we look at their vanishing set now in difference K algebras rather than K algebras, but we still have that for every difference algebra R, we want this set to be a group. So again, we have this group structure, which is reflected in Hopf structure. And we can consider the representing algebra or the coordinate ring for a difference algebraic group, which is now a finitely difference generated difference Hopf algebra. And we'll use curly brackets to denote this one to show that we're working in the difference setting. So yeah, hopefully you're happy. An algebraic group is the zero set of polynomials, and a difference algebraic group is the zero set of some different polynomials. We can see some immediate examples of this. If we're just taking n to be 2, so we have two endomorphisms on our underlying ring, we can consider the functor which takes a zero set of this linear polynomial in just one variable G. Hopefully you're happy that for any difference K algebra, G of R would be an additive group. And actually any linear polynomial in our difference polynomial ring would define some additive difference algebraic group. We can also see an example of a multiplicative group. So say we take all the invertible elements in our difference algebra that satisfy this relation where we have some monomial equal to 1. Really to write this in the form of kind of VF, where it's strictly the zero set of some polynomials, rather than say, oh, let's take the invertible elements, we introduce this element H, which is going to be the inverse to G. So we set that G needs to be invertible and that it needs to satisfy this monomial relation. And yeah, hopefully you're happy that this would define a multiplicative group. And any monomial set equal to 1 can give us a multiplicative difference algebraic group. And we just have the same argument that we had with closed subgroups, but now we have difference closed subgroups. So again, we have two difference algebraic groups, which are of course defined now by some difference polynomials. And if, for example, the defining polynomials for G are contained in the defining polynomials for F, H would be a subfunctor of G. And in fact, all the kind of structures are compatible, and H is in fact a difference closed subgroup of G. Similarly, we don't, when we're kind of considering H just as a difference closed subgroup of G, there's no need to reimpose those polynomials F. We can just consider the kind of extra restrictions that we need, which we denote by this IH, or the defining ideal of H as a difference closed subgroup of G. Again, because H has group structure, this defining ideal has Hopf structure. It's also a difference ideal in that if some polynomial vanishes everywhere on H, of course, any transform of that polynomial will also vanish everywhere on H, which is why it has this nice difference structure as well. So again, we get this one-to-one correspondence between difference closed subgroups of G and difference Hopf ideals of the coordinate ring for G. Okay, so we have algebraic groups and we have difference algebraic groups. And we're going to be interested now in a certain subset of some difference algebraic groups, which we kind of can build from algebraic groups. So we're going to do, suppose we have an algebraic group over a difference field. So our field has difference structure, but the algebraic group doesn't. Algebraic group is just defined by some polynomials. Well, hopefully you're happy because K is a difference field, we can consider the ring of difference polynomials over K. And implicitly, any polynomial is a difference polynomial, which means we can consider the difference algebraic group defined by F when we consider F to be a set of difference polynomials. We will denote this difference algebraic group that we get from G by this sigma K G, but it works very similarly to G, but it now takes the vanishing set of F in a difference K algebra rather than just a K algebra. And we'll see an immediate example of how this would work. We're going to now kind of restrict, whenever we talk about an algebraic group, we're just going to be considering the general linear group, but any of these constructions can be done for any algebraic group. So we're going to have our sigma field K, and we're just going to use X to denote the entries of an M by M matrix. So then we know the general linear group, it takes a K algebra and returns the group of invertible matrices with entries in this K algebra. And we can say it's defined by this polynomial where we set that the determinant of the matrix has an inverse. Well, then when we look at the difference algebraic group that we get from this, it now takes a difference algebra and returns the set of invertible matrices with entries in this difference algebra. So it's defined by the exact same polynomial, but just now we're considering it as a difference polynomial. When we look at the coordinate rings, the coordinate ring for GLM, I'm now just replacing Y by 1 over the determinant of X. The coordinate ring is just the algebra generated by X and 1 over the determinant of X. But then our difference K algebra that we have with the curly brackets here is it's difference generated by X and 1 over the determinant of X. So it's generated as a K algebra by X, 1 over the determinant of X, and every transform of each of these. So we have these kind of difference algebraic groups now which we've kind of made from an algebraic group. And we know a lot more about the structure of these than we do just a standard algebraic group, difference algebraic group. But luckily, we have this proposition, which is that any difference algebraic group can be embedded into a difference algebraic group of this type, and in particular into the general linear group. So I might call this sigma k GLM, the difference algebraic general linear group. So yeah, we can use now the facts that we know about the structure of sigma k GLM, and we can use it kind of to tell us things about this group that we've embedded into it. Recall that because G is a difference closed subgroup of sigma k GLM, it's defined by some difference Hopf ideal of this difference algebra that represents sigma k GLM. So our goal in the paper and for this talk, well, one of the goals is to prove that this difference Hopf ideal is finitely difference generated. Of course, it's an ideal in a quotient polynomial ring in infinitely many variables. It's highly unlikely it's going to be finitely generated, but we will show that because it has this nice structure, that it is finitely difference generated. So essentially, that's equivalent to saying we can define any difference algebraic group as a subgroup of the general linear group by finitely many difference polynomials. We'll just see an example of this embedding. So we've been considering this multiplicative group defined by this monomial. So G of R here. When we're considering G as a subgroup of the general linear group, just GL1, we don't need to then kind of assert again that G is invertible. That's already kind of put in place by the fact that we're working in the general linear group. So G is defined as a subgroup, as a difference closed subgroup of this difference general linear group, just by this monomial subtract 1 that we have. And it's in fact defined by the difference ideal that's difference generated by that polynomial. Okay. So in order to prove that these defining ideals are finitely difference generated, the way that we're going to do that is kind of cut up this ideal using all this structure that we know on sigma k GLM. So this is where we lead into what we're going to define to be the Zariski closures of our difference algebraic group, and then we will talk about the results that we get on these Zariski closures. So we're going to recall we have this difference algebra representing the difference general linear group. And it's represented by the difference polynomial ring in the variables, all the entries of the matrix X and one of the determinant of X. So as a polynomial ring, it's generated by X, one over the determinant of X, and also every transform of X and every transform of one over the determinant of X. And what we're going to do is we're going to kind of put up this difference polynomial ring that we have into a lot of polynomial rings. The way that we're going to do this, we're going to define a natural order on our set of transforms. So as we said, any element in T sigma can be written in this nice form because of the fact that our endomorphisms are pairwise competing. So we can define the order of any transform to be the sum of its indices. Therefore, it makes sense we can consider all of the transforms up to a certain order, which is exactly what we're going to do. So for each natural number I, we're going to consider the polynomial ring in X, one over the determinant of X, and every transform of X and one over the determinant of X up to a certain order. So where our difference polynomial ring had every transform, we're considering all the transforms up to a certain order. And we're going to call this the coordinate ring for GLMI. We're going to, hopefully you can see that that our difference algebra is the union of each of these algebras that we have. And each of these algebras is the representing algebra for some algebraic group. Remember here, because we've kind of almost gotten rid of our difference structure, we're dealing with just algebras and algebraic groups. And we essentially get the product of lots of copies of GLM. And the number of those that we get is the number of transforms of order less than or equal to I, which combinatorially we can see the number of those is I plus n choose n, where n is our number of endomorphisms. So yeah, we have this rich structure on GLM now. We have the algebraic group. We have these kind of growing copies of this algebraic group for every natural number. And then as we almost tend to infinity, not quite because we're now working in difference algebraic group, but we get this kind of difference algebraic group from all of these algebraic groups. And we can use the fact we know a lot about this, and we know that every difference algebraic group can be embedded into this. So for any difference algebraic group, we have a difference Hopf ideal of our difference algebra, which is actually then a difference Hopf ideal of this union of this infinite union of K algebras. And so we can, for each natural number, we can kind of put our difference Hopf ideal to look at just the difference polynomials up to a certain order. So yes, we'll see an example of how this works exactly here in a second. But we have our defining ideal for a difference algebraic group, and we've almost cut it up into the defining ideals of lots of algebraic groups. So yeah, each IGI, because the defining ideal for G is a difference Hopf ideal, each defining ideal for GI is a Hopf ideal of that corresponding GLMI. So it defines a closed subgroup. So now we previously had this like building up for GLM, and now we've kind of shown that we can use that to have this almost building up for any difference algebraic group using the embedding that we can get. And we call this sequence of subgroups and closed subgroups the Zariski closures of G in GLM. We'll just see an example of these defining ideals with our example that we've been going back to. So if we remember, we had this Hopf ideal generated by this monomial subtract 1. This polynomial has order 4. So if we intersect IG with the polynomial ring up to order 3, we're going to get nothing. It's just going to be 0. But for anything greater than 4, we're going to have not just this polynomial, but every allowed transform of it. So yeah, for any I less than or equal to 3, when we try and look at the polynomials in IG up to that order, we're just going to get nothing. But after that, we get not just our polynomial that we started with, but every kind of allowed shift of it, like as big as we can get while being in that, while looking at that polynomial ring of indeterminates just up to a certain order. And so these would be the defining ideals for some closed subgroups of these products of GL1. Okay. Yeah, so we have the each of these ideals and their Hopf ideals, they have all the polynomials up to order I. So hopefully you're happy that we have this inclusion. Each one is contained in the next one, but also a polynomial of order I. Any like shift of it using one of the basic endomorphisms is going to have order I plus 1. So we also get that every kind of basic endomorphism applied to this ideal is contained in the next one. So yeah, we have this kind of infinite chain of Hopf ideals. We saw in just the previous example that it looked like once we included that defining polynomial that we had, all the later polynomials would just kind of shift of that. So what we're actually going to see is that this kind of chain that we have of Hopf ideals, although it doesn't become an equality at any point, it does stabilize with respect to our endomorphisms, to our basic endomorphisms. And this is exactly what we see here. When we have each of these Hopf ideals, which are the polynomials up to order I, at some point, for large enough I and n, we're not actually getting any new polynomials, like truly new. We're getting either the polynomials of a lower order or the shifts of them, or some combination of these. So we get this really strong kind of stabilizing of this growing chain of ideals. Yeah, immediately from this, well, when we can then find some natural number that difference generates our defining polynomial Ig, and we can call it M, a different M to the GLM. But essentially, we know that this IgM would be it would be an ideal of a polynomial ring in finitely many variables. So of course, we know that it's finitely generated. And this actually tells us that then Ig is finitely difference generated. So this is one of the things that we wanted to see, is that any difference algebraic group can be defined as a subgroup of the general linear difference algebraic group by finitely many difference polynomials. And as I mentioned earlier, this then gives us a class of difference ideals which are finitely difference generated. It's a bit wordy. Essentially, it's kind of the same result that we've just had, because any difference Hopf ideal of a finitely difference generated difference Hopf algebra that corresponds to a difference algebraic group. So we can see that it's the defining ideal for a difference algebraic group, and so it's finitely difference generated. I should say that the theorem that we have here was proven in a paper in Vibma in 2022 in the ordinary case. And then this paper on arXiv that I've released is we use induction on the number of endomorphisms to generalize this to the partial case. It is kind of fiddly to do. We have to kind of loosen the definition of Zariski closures and introduce a more generalized notion in order to apply this induction. But of course, this is satisfied for the more generalized notion, so it's satisfied for these Zariski closures. We have this chain, well, it's not quite a chain, so we have this sequence of algebraic groups, and in difference and differential algebra, dimension polynomials are a very rich topic. So because of each of these GIs is an algebraic group, it makes sense to consider its dimension, which is just the dimension of its the Krull dimension of its representing algebra. And we find that because our ideals, our defining ideals for these algebraic groups stabilize in this nice way, the dimensions of the algebraic groups stabilize in a nice way as well. And that is exactly means that we can find some polynomial such that for large enough I and n, it tells us the dimension of our algebraic group GI. In particular, we can find that this is a numerical polynomial, and that it has degree less than or equal to the number of endomorphisms that we're working with. While it doesn't make exactly sense to talk about the dimension polynomial of a difference algebraic group, because this is defined based on our embedding, the degree and the leading coefficient of this polynomial are invariants of the difference algebraic group G. They don't depend on the choice of embedding. And so we will see that they mean we can define something nice for our difference algebraic group. Firstly, we'll just see an example of finding one of these these dimension polynomials for this group that we keep going back to, this multiplicative group. We said that for any I greater than or equal to 4, the defining ideal had this form. And so hopefully you agree with me that we can find that the dimension of the algebraic group is like this. We can use some combinatorics to find the exact form of this. And so we see that the dimension polynomial for this multiplicative group that we've been looking at is 4 times t plus 1 minus 6. Now, if you don't deal much with dimension polynomials or numerical polynomials, this might look like an odd way to write a polynomial. But writing it like this helps us to read off some nice invariants easier. So if we have some dimension polynomial of the Zariski closures of our group with respect to some embedding, we can see that phi is a numerical polynomial. So while the coefficients of phi t are phi t is a polynomial over the rationals, the coefficients could be rational, we can write it in this nice way where we get these CJs, which are actually going to be integers, not rational numbers. So we can see, we know that d is less than or equal to n. We know that the degree of this polynomial is less than or equal to the number of endomorphisms. And essentially writing our polynomial in this form means that we can read off some nice invariants of our difference algebraic group G. So we call the degree of the polynomial the difference type of the difference algebraic group. We call its leading coefficient, when it's written in this binomial basis, the typical difference dimension of G. And then the difference dimension of G is either 0 if the degree of our polynomial is less than the number of endomorphisms, or it's the same as the typical difference dimension if our difference type is equal to the number of endomorphisms. Hopefully you are happy if I say that an additive difference algebraic group corresponds to a difference module in some nice way. And there's been a lot of research into dimension polynomials of certain different structures, and particularly in Levin's 2008 book, Difference Algebra, there is these invariants of a difference module are defined. Luckily, when we look at this correspondence between additive difference algebraic groups and difference modules, we actually get that this dimension polynomial, and in particularly these invariants of the difference algebraic group, agree with that of the corresponding module. So this is a generalization of those results for difference modules. Finally, we'll just read off with this example that we've been working with. We found the dimension polynomial for it earlier. Because we have 2 endomorphisms, but the degree of the polynomial is 1, this tells us that the difference dimension is actually 0 because our difference type is less than the number of endomorphisms. So we have difference type 1, and we can read off that our typical difference dimension is 4. So just to summarize, we use this nice fact that any of our difference algebraic groups can be embedded into this general linear group, and this opens up, we can use this structure of the general linear group to prove this very strong kind of stabilization property of these ideals, which then tells us that any difference algebraic group is defined by finitely many difference polynomials. And then we can also find this dimension polynomial, which allows us to define the difference type, typical difference dimension, and difference dimension of a difference algebraic group. So yes, thank you very much for listening. I look forward to any questions.
Thank you very much, Ola, for this very nice and interesting presentation. Are there any questions or remarks? Please just unmute yourself or write in the chat, which I'm opening now. So the chat. Maybe I start with a quick question. You mentioned the transition from the ordinary case to the partial case. You do an induction where you somehow said you generalize the structure, or you massage the objects a bit. I'm not sure exactly how
Yes.
it works. So
Yeah.
can you give
Yeah.
a couple of more hints, maybe, how you do the induction?
Yeah, exactly. So, thank you. These essentially what we do to do the induction, we look at kind of the things just of the highest order. So we have these ideals which have everything up to order I, and we can look at the things kind of just of that highest order, and we see that those form some kind of n-1 group. But we need to kind of loosen the result where Zariski closures, the defining ideals have all the possible defining polynomials up to that order. We have to kind of loosen that and say we want some polynomials, they still have to satisfy some nice results, but some, say a polynomial of order I can come in kind of late. It could come in at the I plus one Hopf ideal, and that allows us to apply the induction to the kernels. Otherwise, these kind of things of order exactly I aren't exactly Zariski closures.
Okay, thank you very much for this further explanation. Are there other questions? Looking at the chat as well. So I will definitely go back to your archive preprint.
Thank you.
Yeah. So there's a question in the chat. What is the difference polynomial of something that I'm going to read in a moment? So for an algebraic group G, we consider sigma lower index k, as you wrote, right?
Yes, yeah.
Sigma lower index, maybe you see that in the chat as well, right? Sigma lower index k of G for algebraic group G.
Yes, yeah, exactly. Thank you very much. Yeah, this is one of the examples that I kind of ended up taking out for time, but yeah, the dimension polynomial of this, it's got order, it's got degree n, which is the number of endomorphisms. So the actual polynomial written in this form is like the coefficient is the dimension of the algebraic group G. And that's kind of the coefficient of that I plus n choose n binomial. So yeah, this difference algebraic group that we get from an algebraic group, it has difference type n, which is almost to say it's full. It kind of uses all of our endomorphisms, and because it has that maximum difference type, its difference dimension and typical difference dimension are both equal, and they're both equal to the dimension of the algebraic group that we started with. Because you can kind of imagine we have I plus n choose n copies of our algebraic group that we started with. If that answers.
I hope this is all right. Otherwise, please ask again. Are there other questions or remarks for Ola? Do you have a next step in your research on that topic that you pursue now?
Yes, yeah, there was a couple of things. I mean, I was looking a bit at it's known the form that any Hilbert polynomial can take, and the dimension polynomials for example, difference field extensions exactly coincide with this set of Hilbert polynomials. So one kind of project is seeing if the dimension polynomials for difference algebraic groups also take this form, which I would guess they do. but also having the difference type of a difference algebraic group. It's one of the kind of steps towards being able to do some kind of Jordan-Holder decomposition for your algebraic group. It allows you to define kind of the strongly connected difference algebraic group. So hopefully we'll be able to use those invariants that I mentioned at the end to do that.
Yeah, sounds great. Thank you very much.
Mm-hmm.
Are there other questions? That does not seem to be the case. Everyone is very happy. So if I remember well, next week we don't have a talk, but in 2 weeks' time there would be the next presentation in the Colchin seminar. So I hope to see everyone again 2 weeks' time. Thank you.
Thank you. Thank you very much for having me.